Hello everyone, I'm Xiangyu. Today I will present our work on switch code generation using program synthesis. This is joint work with many collaborators from New York University, Rutgers, Princeton University, and National University of Singapore. Programmable network device has become quite widespread, and they also run at a fairly high speed. For example, Linux Alveo run at 100 gigabits per second. Mellux run at 100 gigabits per second, and Barefoot Tofino run at 6.5 terabits per second in aggregate. And this is exactly the target we want to generate code for it in our project. It is easy to get started with programming these devices. For example, you can read a tutorial or you can attend a workshop. But writing fast packet processing programs that fit within resource constraints is really hard. There are two main approaches to writing fast programs, but none of them is easy to implement. The first one is to handcraft fast programs, but this requires optimization by experts who are familiar with each of the underlying hardware architecture. For example, they must be aware of the lookup table for FPGAs, cache and memory hierarchy for SmartNICs and CPUs, arithmetic logic unit or ALUs for switches. The second is to rely on the compiler to do code generation automatically. I totally agree that the compiler itself will definitely elevate the difficulties of generating such code, but building the compiler itself needs significant engineering effort, which is both time-consuming and money-consuming. For example, Intel, AMD, they all have large compiler teams to build a compiler for each of their underlying hardware architecture. Second is because the packet processing hardware is unique. Sometimes it's really hard for us to build a team for newly emerging hardware architecture. So this paper represents a new approach to do code generation for programmable switches. Hopefully I have convinced you writing and compiling fast switch programs is hard. Let's take a look at how tricky it can be to develop such a compiler. A programmable switches compiler have all or nothing feature, which means it either fit a program into the hardware or reject it. So I will give you an example written in Domino language. For now, it is sufficient for us to think about Domino program as a C# language and turn it into the machine code, which will be finally run in the programmable switches. The compiler will figure out the choice of opcode, which input will be used for a particular ALU and the value of multiplexes. We can also think about the Domino program as the action portion inside a P416 program. So what could go wrong with setup? The Domino's compiler produces different outcomes on semantically equivalent programs. If we write a program in this way, then Domino fails to generate code for it. However, if we rewrite in this way where we move the assignment of filter 1 and filter 2 out of the if-else statement, then Domino can generate code for it, which means Domino's compilation result is inconsistent for semantically equivalent programs. We can develop a specific algorithm to fix this particular issue, but other issues may still happen. This is similar to an arm race between one programmer writer and the compiler designer. This butterfly effect also happens in some other P4 compilers as well. Let's take a look at why this could happen in a lot of rule-based compiler. The rule-based compiler usually use a rewrite rule to rewrite a given program into a format which is easier to generate the machine code. The Domino will write the given program into an intermediate representation in this stack, where the blue rectangle represents the computation for stateful variables, and the white rectangle represents the computation for packet fields. And each of these rectangles should be mapped to one particular ALU. In this version, the ALU is really simple. That's why Domino can generate code for it. However, if we write in this way, then the DAC file looks really complex. That's why a specific ALU cannot express the portion which is circled by my red circle. That's why Domino failed to generate code for it. In response to the above concerns, here's our contribution in our project. We leverage program synthesis to do code generation, and we develop many domain-specific synthesis algorithms. The most effective one is slicing. And we also try to run our generated code in two backends. The first one is a pizza simulator, and the second one is a Tofino's ASIC. At a really high level, Program synthesis is to automatically generate a program that satisfies a specification. A program synthesis takes two inputs. The first one is the search space represented by a partial program, and the second one is the specification. Then both of them is fed into an exhaustive search algorithm to output a completed program that satisfies the specification, or return infeasible if there is none. In our project, we use search space to represent the machine code skeleton and use specification to represent the high-level language program. The exhaustive search algorithm or program synthesis tool we use in our project is Sketch. We believe program synthesis can be used as an enabling technology for packet processing compilers. Let's take a look at a concrete example in Sketch. Suppose we want to add the input to itself 3 times, which will be regarded as the specification. And if we consider this partial program, well, question mark here is a hole which represents an unknown constant integer. Then Domino can generate code for it by setting the whole value to be 3 to get the completed program. However, if we consider this partial program, then Domino cannot find any solution for it. That's why we call this partial program infeasible. So suppose we have 2 people. The first one is a programmer and the second one is a compiler developer. The programmer will write a program in Domino language, which will be turned into the Sketch specification, and the compiler developer will write a partial program which represents the programmable switches capability. Then both of them will be fed into a Sketch program synthesis engine to output the completed program and finally turn into the programmable switches machine code. We call this whole structure chipmunk. Let's take a look at chipmunk in more detail. Still, we have these 2 people. The programmer will write a packet transaction program in Domino language because Domino preserves the transactional semantics. He will use the state variables like count to represent the persistent switch state, and the packet field like packet.sample to represent the packet header. The compiler developer will write a partial program for programmable switches. Stateless ARU is used to modify the packet header, and a stateful ARU is used to modify both persistent switch state and packet headers. The packet header vector is regarded as a container for all packet headers. The input marks will determine which packet headers were used as the input for any ARU, and the output marks will decide which output will be passed to the next state. The structure is similar across stages. When we have both program and partial program in hand, we will feed them into the chipmunk to output the machine code for programmable switches. However, synthesis will be really time consuming. Sometimes it takes several hours, sometimes several days to get the compilation result because the search space might be very large. It is similar to you want to pick out a needle out of a huge stick. You have to use a magnifying glasses to find it. Nobody wants to waste such a long time to get his or her compilation result. That's why we leverage many domain-specific algorithms to speed up the whole process, including slicing algorithm, constant synthesis algorithm, canonicalization algorithm, and scaling up synthesis to larger input ranges algorithm. The most effective one is slicing. So, what is the specification for code generation? Suppose we are given a packet plus state vector which store the initial value of packet fields and stateful variables. They will be fed into the program which written in Domino language and get the output which stores the updated value of packet fields and state variables. They will also be fed into the implementation on switch pipeline and get the output vector. When we compare each member or each component inside these 2 vectors, their value should be exactly the same. So here's come to our slicing algorithm. We only need to let our slice to guarantee some portion or some component inside these packet plus state vectors are the same. For example, in this case, we only need to guarantee the first member inside the packet vectors are the same. Here are the last member in the packet vector. Here are the first member in the state vector and the last member in the state vector. In general, we want to divide our slicing algorithm into 2 phases. The first one is divide phase, which means we divide everything into n slices, and each slice only take care of some portion inside the packet plus state vector. And after the divide phase, we go to the conquer phase, where we gather different portions from each slices and combine it to a new packet plus state vector. When we compare the packet plus state vectors, their value should be correct. There are a lot of benefits for this slicing algorithm, like they significantly reduce the synthesis time because the search space in each slice is smaller. However, there is no free lunch. The cost might be we have to use more ARUs per stage because we cannot share common computations across stages. But usually, a programmable switch has a lot of ARUs per stage. That's why this is not a big problem. So how can we use slice? Let's take a look at this example. We will split the given domino program into 3 slices, and each slice only take care of one particular packet field or state variables like packet.f1, packet.f2, or count. And we will use sketch to output the implementation for each slice and group the implementation together so that the group version of machine code can fully express the functionality from the domino program. However, the naive slice cannot work for every benchmark. It may fail when we try to do the state modification. So let's take a look at another example where we add the count value by 1 and set the updated of count value to packet.f. We have two slices. The first one take care of the packet.f and the second one take care of count. So what will happen in this setup? Suppose both of them have the initial value 0. When the first packet goes through this pipeline, the count value in the second slice will be added by 1. That's why its value becomes 1. However, the count in the first slice keeps the same. That's why the packet.f will be set to the initial value of count in the first slice, which is 0. When a second packet goes through this pipeline, count value will become 2, but packet.f still keeps 0. When n packet goes through this pipeline, count have already updated to n, but packet.f still stays at 0. That's why we can say the slice for packet.f is incorrect. So how can we solve this problem? We have to track all variables which influence the output member within a particular slice and add those state vectors into the specification. Still, we look at this example. We found the count, updated value of count, will determine the final value of packet.f. That's why we group them together and put them into one particular slice. So what will happen in this influence tracking algorithm based slicing algorithm? Then they still have the same initial value. When the first packet goes through this pipeline, count will be added by 1, and the packet.f will set to the updated value of count, which is already 1. When the second packet goes through this pipeline, both of them will become 2, same as n packet goes through this pipeline. That's why we call this algorithm is correct, which means if the output variable of a slice depends on a state variable, then the state variable must be part of the specification. I will show more details in our paper. So for the backend for Chipmunk, we developed 2 backends. The first one is a pizza simulator backend based on the Banzai machine model, because this is used to compare against the Domino's compilation result. And we also try to run in Tofino's ASIC because we really want to show that our generated code have already the ability to run in real hardware. We also designed Chipmunk to be retargetable so that if someone gives a new instruction set, we can easily support it to do code generation for that setup. For evaluation part, what is our baseline compiler do? We compare Chipmunk against Domino's existing compiler. That is because Domino use some handcrafted rules to translate Domino program into machine code. We also consider some other alternatives, such as compiler from chip vendors like Belfort, but they have not supported Domino's transactional semantics. We hopefully this can give them some insight to merge our idea into their compiler design. We also consider some open source P4C compiler, but they only support software packet processing target with a totally different architecture. What is our metric and benchmarks? The metric must be the compilation result, which means whether Chipmunk or Domino can successfully generate code for given input. If they both of them get successful compile. Which one use fewer resource? Of course, the fewer resources used, the better. We pick up benchmark programs written in Domino language, but we cannot directly use these benchmarks because these benchmarks were written to ensure they get successful Domino compilation. And we also confirm like Chipmunk can successfully compile them as well. So purely compile Domino and Chipmunk in these benchmarks is useless. But we really want to ask this question: if you mutate these programs, will Domino and Chipmunk still compile them? Theoretically, the answer is yes, because if a program gets compiled, the equivalent program should also have the same result. But empirically, it totally depends on how good Domino and Chipmunk are in finding machine code to implement a Domino program. Actually, Chipmunk successfully to generate code for all the benchmarks. We have 14 benchmarks, and each of the benchmarks will generate 10 mutations. But Domino failed to generate code for most of them. As for the resource constraints, Chipmunk use fewer stages than Domino, which means the combinatory search algorithm has better ability to figure out the possible whole configuration to fit within resource constraints. As for the compilation time, Chipmunk, this is Achilles heel for Chipmunk because Chipmunk use several minutes, sometimes several hours to get our benchmark to get compiled, but Domino only use several seconds. The worst case take 2 hours, but most of them finish within 5 minutes. We also try to compile all the benchmarks into the Tofino, and we successfully run 10 out of 14 benchmarks in our Tofino switch. The reason why the number here is different from the previous table is because the ARU supported in Tofino switch is different from the ARU supported in the pizza simulator. However, the remaining 4 benchmarks failed to run in Tofino switch. We guess it should be their functionality cannot be expressed by the given Tofino switch, but we haven't theoretically proved it. As for the spin-off effect from slicing, we divide our origin time by the slicing time and get the speed up number. On average, we get 51 times speeding up from the slicing algorithm. To conclude, we successfully transplant the program synthesis to code generation, and we prove this can play an important role in code generation for fast packet processing. We also believe program synthesis can enable fast packet processing like what SET and SMT solver have enabled in network verification. Many domain-specific speeding up algorithms can really help make this whole process feasible. With that, I conclude. Thank you.